So the interval of convergence is almost always what we're looking for. This is our domain, which is just the set of x values for which a series will converge. So it's going to be whatever interval. And so let's do an example. Let's say we've got a series. The interval is going to be different than the radius in some sense, only when we have a power series, or at least primarily when we have a power series or a Taylor series that's centered at a different point. So let's say we have something like n times x minus 2 to the n over, and let's say 4 to the n. So I guess I didn't define the radius of convergence. We'll define it as we go through, and I'll show you where we kind of pick out the radius and then how the radius and interval are tied together. So essentially what we want to do is essentially just find the interval of convergence. And we do this through the ratio task. So our a n plus 1 gives us n plus 1, x minus 2 to the n plus 1 over 4n plus 1. We compute the ratio of this guy with the given term, so n x minus 2 to the n over 4 to the n. So it's absolute value of an plus 1 over an. And I think most people are getting pretty good with these at this point, most of these ratio tests. So of course we multiply by the reciprocal. And then we simplify. So I can factor out n quantities of x minus 2. So I'll have one more in the top there. And actually, mind the absolute values. We still need our absolute values because our x's could potentially be negative. The other thing, we've got 4 powers, or n powers of 4 that we can cancel out. And then this n plus 1 over n kind of hang out. So this is just the algebra at the moment for this ratio that we just computed. We found that this guy simplifies to n plus 1 over n times, we've got 1 power of 4. So I like to leave the constants to the left. We have an n plus 1, an n, and then 1 power of 4 in the denominator, and then what was left, 1 power of x minus 2. So this is just a simplification of that. And then we declare this to be less than 1. So we set that equal to, or set that less than 1, because I know that when this ratio is less than 1, it'll converge by a geometric series. Okay, so I'm running out of space, so let me rewrite that. And of course, I should say we want the limit of that to be less than 1. So we do got to still take our limit to infinity of n plus 1 over n times a fourth times x minus 2 to be less than 1. And so, of course, when we take our limit, the polynomial terms aren't going to matter much. It's just going to go to 1. And so what are we going to have? We're just going to have 1/4 times x minus 2 is less than 1. And the goal with all of these is to essentially isolate the x term. So this next step is what gives us the radius. If I multiply both sides by 4, so that's just the positive constant is 1/4, which means I could pull the 1/4 outside of the absolute value and multiply the 4 over. Positive constant isn't going to change the value of the inequality, and we get something like this. And so once we're here, when we have like an absolute value of x or absolute value of x minus a value is less than some number, this guy here is our radius of convergence. This guy here, so remember it's always x minus something. Whenever we have x minus a constant, what we're saying is that I'm looking for the set of x values whose distance from that value, distance from that number is within a certain radius. So this is the center of the interval. Can you guys see that? Is that marker coming up? It's kind of light. Use a darker color. So where does this kind of come into play? Let's go ahead and solve this out. Whenever we have absolute value of x minus 2 is less than 4, we get x minus 2 is less than 4 is one equation, but it also has to be bigger than negative 4. And then we add 2 to every side, and we'll get negative 2 is less than x is less than 6. So our interval is this guy. But I guess we should put a point here. You need to check the endpoints. So I know at least those values in between negative 2 and 6 are going to be included in the interval of convergence. And you can see this essentially just by plotting it on a number line. So let's try to do it accurately. So we've got minus 2, 1, 0, 1, 2, 3, 4, 5, 6, 1, 0, 1, 2, 3. Let's plot 2 there. And so where are we converging at? We're converging at this range. And I put round brackets there because we might need to check the endpoints. One of them might be closed. But where is the center of this? Graphically, you can kind of see 2 is right in the middle. And what's the radius? It's a distance of 4. Does that make sense?
Yeah, that makes a lot of sense.
Yeah. So it's, of course, it's just a, I mean, we call it the radius because it's basically a one-dimensional circle. One-dimensional circle is just kind of a line segment that's centered about some point. And I guess the only thing left to do, let's check the endpoints just for practice. So we check our original series. We've got, so if x is minus 2, we will have the sum of n minus 4 to the n over 4 to the n. And what's going to happen with this guy? This is just going to be the sum of n times minus 1 to the n. And so it will diverge. So the terms aren't even going to 0 there. So it's going to go off to infinity because of that n in the numerator. It'll diverge for that guy, and it'll probably diverge for this other one since I have this extra n. And we can check. So we'll have n. 6 minus 2 gives me 4. course, is sum of n, and that will also diverge. Diverge. Sorry, I didn't write that on the screen. So of course, always check the endpoints. It can, they can diverge for both endpoints. They could converge for both endpoints sometimes. I guess it's a little more rare. We'd have to work to get them to converge for both endpoints. A lot of these, like if this n were in the denominator, then this series would converge by alternating series, but it would diverge on the other endpoint. So always be careful. Always make sure you're checking those. So our interval in this case, we want to write it in our bracket notation. It's just -2 to 6. Any other questions on that guy? Is anyone still writing, taking notes? Okay. So let's jump back into this error estimation. So go ahead and pull that up so you guys can follow along. And you can see it if you would like. If you go to the schedule, it is on the schedule for, let's see, where was it? Matching, recursive sequence. It's on the schedule for today, but it's listed as the activity. So activity, Taylor polynomial, remainder estimate practice. And yesterday, we started to use this formula. So the formula is written at the top. Let me write it here at the top of the notes. Make sure I'm on screen here. So we've got our absolute value of Rn is less than or equal to m over n plus 1 factorial, absolute value of x minus a to the n plus 1. And again, if a is like the center point where we're centering our Taylor polynomial, this absolute value of x minus a really means how far away is my x value from that center. And then we have to scale it. We actually have to raise that to the n plus first, because the more polynomials that we take, the closer it should be, more accurate. And then on yesterday, we saw that we have our e to the x. We took, sorry, that would be x over 1 plus x squared over 2. And so we approximated e to the 1 is about 1 plus 1 plus 1/2. And then we use our error estimate to figure out how close we are. And what we did was we said, since we used 2 derivatives, we found that R2 is less than or equal to, so remember that m is an upper bound for the next derivative. On some interval between x and a. So nicely enough, if our function is e to the x, doesn't matter how many derivatives we take, it's still going to be e to the x. In this case, the next derivative, the n plus first derivative, would be our third derivative. Our third derivative was e to the x, and so we bounded on, our interval was, so our a is 0 and our x value we care about is 1. You can use, I guess we can use closed interval. It's probably better for that. Open interval, just as good. So we chose our m. Because we know e to the x was increasing, we chose our m equal to 3. And we talked about how the closest m we could get should be e to the 1, but that is literally the value we're trying to approximate. And since we don't actually know what that is, we kind of pick a closer integer that I know is bigger than the function, bigger than the value, but more easy to compute. And so what we found was that the error is going to be less than 3 over 3 factorial times our x value is 1. And so we found that our error is going to be less than 0.5. So of course 3 over 3 factorial gave me 1/2, and no other constants or anything to multiply out since this term's just 1. And so we just found our margin of error is within 1/2. So that's pretty good. We kind of know from mainly people telling you that E is 2.718, something like that, right? But you've had to take that for face value, right? Either type it into a calculator or type it into Wolfram Alpha, some other program, or your math instructor says E is about 2.718. How can we verify that, or how can we compute that ourselves? Well, using these Taylor series. So let's move on to the next part. Let me read it real quick. So part 2 says, in this problem, we will know the value of x and the accuracy we're going for, but now we want to figure out how big of a polynomial should I use. So in this last one, our error is 0.5. That's actually kind of big, right? Especially if the value we're approximating is 2.5. If our error is 0.5, that means I know that E is going to be between 2 and 3, which isn't as accurate as maybe we'd like. So number 2, we want to improve our accuracy. 2A says we want the error to be within 0.1. So anytime it says we want our estimate to be within a certain value, to be close to a certain value, or we want the remainder to be less than a certain value, this is the value we are going to compare our remainder formula for. And of course, the other part of the question that'll give away that this is the process, it'll say something like find n, or find how many, let's read it, how many terms in the Taylor series do you need to add up? So it'll say something like that. It'll say find the number of terms within the Taylor series. So the easiest way to do this is to just simply start off with our equation. I know that the number of terms I'm going to take is just going to be n. I don't know what that n is going to be. It's something we need to solve for. And we can just start off by writing out the generic formula. And so I know that the remainder is at least less than this. So if I take this guy and set it less than the error we want, we'll be good. And so now I only have to solve this right side inequality. Let's fill in our values now. So we still know that we are trying to approximate e to the 1. So that implies that our x is still 1. Our a is still 0, which is where the Taylor series is centered at. And what should our m be? In this case, we want m as an upper bound for the n plus first derivative on the interval in between a and x. So in this case, 0 to 1. And so with this part, we always have to come up with a formula for the n plus first derivative. We haven't had to do this too much yet. We've kind of seen it for taking general Taylor series and finding the general coefficients. Luckily, in this case, it's going to be easy, right? Because, well, what is the first derivative? E to the x. What is the second derivative? E to the x. What is the n plus first derivative? Our function is nice enough that it is e to the x. So finding the formula for the derivative for this guy, easy. Our fn plus 1 is e to the x. And just like we did in the previous case, well, since the function is e to the x on the interval 0 to 1, we just need an upper bound for our function. And of course, I know this will be EU that we're trying to approximate. And so our upper bound maybe that we choose again is a nice integer close to that, so 3. So our m in this case, again 3. And now we just want to plug everything into this equation. We know our m, we know our x, we know our a, and we are solving for n. N is the number of terms. So we get 3 over n plus 1 factorial times x minus a was just 1 minus 0 to the n plus 1. And we need that to be less than 0.1. With some of these estimates, as we've seen, like it can get, sometimes you got to use calculators depending on how this function works out, especially with these factorials, and if this guy ends up being a little weird as well. Luckily enough, it's not too bad of an equation, so we can actually just do this guy by hand, by guessing and checking is essentially the method you first want to try whenever you're working with these factorials. And I'm going to change this to a fraction. So 0.1 is just 1/10, because I'm going to multiply the n plus 1 over, multiply the 10 over to the other side, and we just get 30 is less than or equal to n plus 1 factorial. So guess and check. What are your factorials? So you should know up to 4, basically. 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, and 4 factorial is just 4 times 6, 24. Beyond that, you know, it takes a little bit of work. 5 factorial, I would have to multiply that by 5. So what's that, like 120? Numbers, of course, get really big really fast. Well, so when are we going to be bigger than 30? We don't even have to compute it. I know that 5 factorial is going to be bigger than 30. And if you want to write it as 5 factorial, we know it's going to be 5 times 24, even just to keep it as somewhat factored. And so I know that's bigger than 30. So at 4, we're not big enough. 5 is where we're going to be big enough, which means we want our n plus 1 bigger than 5. So this is just a point to be careful with. Remember that it is n plus 1 quantity. That's the whole thing being factorial. So the object being factorial needs to be 5 or more. I guess we should say bigger equal to 5, because at equal to 5, we're still bigger than 30. And so when we solve for n, bigger equal to 4. So to be within this accuracy of 0.1, we need to take a degree 4 Taylor polynomial. So keep in mind our n is the degree of the polynomial, not the number of terms, because the number of terms, remember, starts at 0. So what is our e to the x Taylor series? It was 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial. So we go up to a degree 4. And to approximate e, now we can just plug in 1 for our x's. So 1 plus x, 1 plus 1 plus 1/2 plus 1/6 plus 1 out of 24. And if we want to keep it in fractions, so this is just going to be 2 plus 1/2 is 12 out of 24 plus 4 out of 24 plus 1. So 2 plus 17 out of 24. And if we want to get a numerical approximation from this, we can plug that in a calculator. What's that going to equal? Let's plug that in. So 16 out of 24 is, what, 2/3? So it should be about 2.7 or something like that. So 2 plus 17 out of 24 gives us, 2.708. And a bunch of 3s repeated. So now we know we are within that accuracy of 0.1. Any questions on this guy? So let's move on to the next part now. Number 3 asks, in this problem, we'll know the nth degree, and we want to know how big x can be to get an estimate. So in this case, it says using a 5th degree Taylor series for sine of x, centered at a equals 0, to estimate sine of x. How large can x be to get an estimate within 0.0005? So let me write down the basics of sine x. Centered at 0. How big can x be to still be within 0.0005? They say, also, I guess we should say, 5th degree. Taylor polynomial. So this is the basics of any sort of problem where we're using a formula. You have to be given all of the bits of information except for one, and then you need to solve for that remaining one. And if you look at the formula, so we know our n in this case is 5. Because we know our 5th, we are always going to be able to solve for m based on the function. So if we plug all those in, what's left to solve in our inequality? We want the error to be less than 0.0005. So again, anytime they say something to be within, want an error of less than a certain value, that's going to be the right side of our inequality. And so what are the only pieces we have to solve left? We can have to find m based on the function. And then the only thing left to solve for is x. So let's first find our m. So remember, our m is our n plus first derivative. So what is the sixth derivative of sine of x, even if you don't know what's a derivative of sine of x, it's going to be cosine. Derivative of cosine is going to be negative sine, and then derivative of negative sine is going to be cosine. And the more and more derivatives we keep taking, it's always going to be sine or cosine. And I guess we could say absolute value as well. So even if you're not sure exactly what the sixth derivative is and don't want to go through the mental math, I know that the derivatives are always going to be sine and cosine, and we want an upper bound for them. And sine and cosine are always bounded between -1 and 1, meaning the absolute value of it is always going to be between 0 and 1. So the most it can be is 1. You can always bound sines and cosines by 1. If you wanted to go through that explicitly, well, if I take 2 derivatives of sine, I get negative sine. If I take 4 derivatives of sine, we get back to where we started. I think we saw this the other day when we were computing the Taylor series. So the sixth derivative, after I take 4 derivatives, we'll be back at sine. 2 more derivatives, we will get negative sine as our sixth derivative. And of course, when I take absolute values, the same thing as absolute value of sine of x. And again, we know that that is less than 1. So we can set this as m. And then the last thing we got to do now is just plug that in and solve for x. So this might be something we need a calculator for. Let's see if we can do it. So we have 1 as our m over 6 factorial. And then we have absolute value of x to the 6th is less than or equal to 0.0005, which is going to be 5 over 10,000. Yeah, so I think we'll need a calculator because we will have x to the 6th has to be less than or equal to 5 over 10,000 times 6 factorial. So 6 times 5 times 4 times 3 times 2. Any easy mental math we can do with this? Let's see, 5 over 10,000 should give me 1 over 2,000. Times 6 times 5 times 4 times 3 times 2. Let's see. So the 5 over 2,000 gives me 1 over 400. 6 times 5, sorry, we canceled the 5. Times 4 times 3 times 2. 4 gives me 1 over 100 times 6 times 3 times 2. So 6 times 3 over 50. And of course, well, none of that's going to matter much because what do we got to do to solve for x? So I just canceled the 2's in that last case. And we're going to have to take a 6th root anyway. That was kind of a waste of time. So absolute value of x less than or equal to 6th root of 18 over 50. I guess we could even cancel out a 2 from the 6 and 5, or 6 and 50. So what's that? 3 times 3 over 25. So x is going to be less than the 6th root of 9/25. Let's go ahead and put that in a calculator to get an actual number. Looks like we are getting 0.84. Let's give 3 decimal places, 843. So what does this mean? This means that my interval of convergence, or at least my, I guess we could call this like the interval of accuracy, whenever x absolute value of x is within that range, and we are centered at 0, so it's not x minus a or anything, and we don't have to normally write, if it were centered at 1, say, it would be x minus 1, and then here we would set up this inequality with x minus 1 in the middle and have to add 1 to find this interval of accuracy. But because it's centered at 0, essentially the radius is the upper and lower bound. And so what does this mean? 0.843, if we had to graph it, we have sine of x. And then we are taking a 5th degree polynomial. So whatever this 5th degree polynomial is doing, it could be doing crazy stuff. Since I haven't actually graphed it and looked at it, it's probably going to come up and bound and then do something like that. Not sure what's going on in the endpoints there. But essentially what it's saying is that as long as my x value, so sine's going to have its peaks at pi over 2. Pi over 2 is about 1.5. So that's going to be too big. 0.8 will probably be halfway in that. So we'll say right there is our 0.843. As long as my x value is within that range, I can plug in that x value into the Taylor polynomial, and then the Taylor polynomial will compute that value for sine of whatever that value is, and we will be accurate within 5 out of 10,000, or 0.0005, accurate up to 3 decimal places. X is beyond that, then the Taylor polynomial is not going to be within that degree of accuracy. Any questions on that? Okay, so I want to get going on the project. I do kind of actually want to mention one more thing from this that we're talking about though before we do. Just because if you look at number 4 and 5 on this activity, number 4 essentially, we want to show that a Taylor series converges for a function. So let's at least practice. Maybe we can finish this tomorrow, because I do want to give you guys some time on the project. I want to at least start number 5 on this, because this is where this first like non-trivial example where we actually have to find a Taylor series for a function by actually finding like a formula for the nth derivative. We actually have the Taylor series for this function, natural log of 1 plus x. But I want to demonstrate, so if we want a formula for like the nth derivative, if this is our function and we want to approximate natural logs of certain values, then like let's say we want to approximate natural log of 2. Then our x would be 1. But we want a Taylor series for this guy, let's say centered at x equals 0. What's going to happen when we start taking derivatives? Well, I get 1 over 1 plus x. My second derivative is 1 over 1 plus x squared. And if we want, we might want to start writing these with negative exponents. So this was just 1 plus x to the minus 1. When I bring down that minus 1, we need a negative out front as well. So I almost lost that. And when I take a third derivative, what's going to happen? We will have a 2 times 1 plus x to the minus 3. And what we want is a formula, if we're going to be using our error bound, let's say for the n plus first derivative. And so we have to just deduce this from the pattern. E to the x was easy because n derivatives is still e to the x. Sine and cosine, a little bit more work, but I know however many derivatives I take of sine and cosine, it's still going to be sine or cosine with maybe a positive or negative out front. But something like this now, we kind of got to keep track of, well, these constants as well as these exponents. So maybe it might be helpful to do one more. So our fourth derivative is going to be minus 3 times 2 times 1 plus x to the minus 4. So what are the patterns we can recognize? I'm always going to have a 1 plus x in there, and the exponent matches the number of derivatives. So that'll be n plus 1. And what's going to go on with the constants? For this guy's negative, this guy's positive, this guy's negative. So it's going to alternate. We've got a negative and positive going on, as well as we've got these 3 times 2. What's going to happen if I take another derivative? I'll have a 4 times 3 times 2. So we've got a factorial thing going on here. But the factorial starts 1 less than the number of derivatives. So here I have a 4th derivative, but I only have a 3 times 2. So if I take n plus 1 derivatives, I'm only going to have an n factorial here. And then I'm going to have a minus 1 raised to either an n plus 1 or n. We got to figure out which derivatives are even, which derivatives are positive, which are negative. So when I take 1 derivative, it's positive. 2 derivatives is negative. 3 derivatives positive. 4 derivatives negative. So even derivatives are negative. So what are we going to want? So if n was 0, it would be 1 derivative, and we need a positive number. So it's actually going to be an n there. That's kind of just guess and check. You could check n or n plus 1, and I would encourage you, go back through it. Let's check it. So when n was 1, that's going to give me my first derivative, since I have an n plus 1. And then, when n is 0, it'll give me the first derivative. So when n is 0, that'll be minus 1 to the 0. It'll be positive. And of course, 0 factorial is 1. 0 plus 1 is my first degree, or negative first degree. Sorry, I forgot my minus sign up there in that exponent as well. And likewise, we can check when n is 1. So if n is 1, that means the second derivative, which will be a negative value with n equals 1. Constant matches up. And of course, I'll have a negative 2 in my exponent. So this is our good formula. So this is our n plus first derivative. And then if we want to bound, on, let's say, 0 to 1. So let's set x equal to 1, which would give me maybe we're trying to compute natural log of 2. I know that my a was 0, since we're just expanding about 0. I guess we would have to plug in, x equals 0 to find our coefficients. But if we want to find our m, we need the full n plus first derivative. And so if we want to bound this on 0 to 1, I need to find an m that is going to be less than that, or that is bigger than this, excuse me. So we want to bound that function on 0 to 1. This one's a little non-trivial now. Now we actually have to do a little bit more work to find our m than what we did on our other ones. So I would say first let's start off with this 1 plus x term. The n's are going to be, m is going to depend on our n, essentially. But our x's, we kind of have to figure out, well, what's going on with this function, right? Just this piece. These are constants. When I take the absolute values, it's going to get rid of that minus 1 to the m. So we can rewrite the equation if we want it just as this guy. And now, well, the constant's a constant. N's always going to be positive, not going to change sign. And of course, we've got absolute values. Let's consider what this function is doing. And again, let's rewrite it as 1 plus x to the n plus 1 in the denominator. And we are on 0 to 1, so the x values we're plugging in are positive. So if we're plugging in positive x values, the denominator is always going to be positive. It is just going to be an asymptote. So our asymptote is at -1, and it's going to look like the use of hyperbolas. It's going to look something like this. But of course, our interval, let's keep the same scale, is going to be 0 to 1. So you got to use your knowledge of the function and how it's behaving to help find an upper bound for m. When's the biggest value of the function? On the interval is at x equals 0, right? Because as x gets bigger, we will just have some fraction, and it will get to be a fraction raised to the nth power. It's going to be an even smaller fraction. So our upper bound in this case, we want to plug in x equals 0, and nicely enough, so for e to the x, we were kind of doing the same analysis. We were looking at the shape of the function, increasing, decreasing, and we realized we needed the right endpoint for the interval since our e to the x was increasing. And then we just came up with an upper bound that was a nice number that we could bound it by because we didn't know e to the 1. In this case, at least, if I check, I know on the left end of the interval at x equals 0, if I plug in x equals 0, of course, we'll just get 1 over 1 to the n plus 1, and it doesn't matter what n is, it's going to be 1. So I know in this case that I can bound this guy by 1. So let's go through that. Let's tie that together. We haven't solved for our m quite yet. So what we're going to do, we're going to have another kind of series of inequalities. This was our function, our n plus first derivative up to sine. I know that this guy is always going to be less than whenever we plugged in 0 for x. So it's always going to be less than or equal to, I guess we should say, just now absolute value of n factorial. Sorry, that's a little slanted. And I still want an m to be bigger than all of that. And this is essentially our defining equation. So I guess we can just write it. We can get rid of the absolute values because we know n is going to be a positive. So for this function, our remainder is going to look like there's our formula. I went ahead and plugged in our a, since a was just 0. M is actually going to be a function of the number of derivatives we take. So we're actually going to have an n factorial over here for m. And so simplifying it, n factorial over n plus 1, it's going to be 1 over n plus 1 times the absolute value of x to the n plus 1. So this could give us a couple things. So we kind of just simplified this expression for the n plus first derivative and for our error bound. So if I wanted to take this, we could now, if we said we need a margin of error of less than 0.1, I could, and if we're given our x, say we want to approximate that natural log of 2, in that case my x was 1, and I could solve for how many terms we got. Or conversely, if I know how many terms we've got, if we know our n and know our error bound, I could solve for how close x is going to be. The other thing we could do is we want to show that the Taylor series converges to the function. Within our interval of convergence. So I guess our interval of convergence, our x value was between minus 1 to 1 was our interval of convergence. In other words, our natural log of x of 1 plus x was minus 1 to the n, x over n, x to the n over n equals 1 to infinity. And so really what we're going to have is something like this. So sorry for the misuse of n's, and actually, you know what? Let's rewrite that since I'm kind of confusing the n's. What was our Taylor series? Let's use k now. Let's say I take an nth degree Taylor polynomial, so we were using little n for the maximum degree. So this was just what our natural log is going to be represented as. So this is our nth degree Taylor polynomial. Then we're going to have some remainder term. And how do I know that if I take n up to infinity, why this equality holds? Well, we need to show that the remainder term goes to 0 as n goes to infinity for all x in the interval of convergence. And so tying this all together, well, I found a formula, at least for the absolute value. We can show that if the absolute value of a function goes to 0, it's going to 0. So you can rewrite this statement if you want to include your absolute values here, just as good. So if we show that this goes to 0 for all x within that interval, we know then that this Taylor series officially converges to our natural log. So all we got to do now is show that the limit as n goes to 0, or excuse me, n goes to infinity, of our remainder term goes to 0. But I know that the remainder term, in absolute value, it's going to be positive. It's bounded by this guy. So this limit, I know, has to be less than this limit. And of course, since we're absolute values, everything is positive. And what's going to happen when I take n going to infinity? It's going to depend on x, but what do we know about x? That x itself, absolute value of x, is going to be between 0 and 1. So know that this is going to be less than or equal to the limit as n goes to infinity, 1 over n plus 1. And of course, if I replace x with 1, we will just get 1 to the n. And then now as the limit as n goes to infinity of 1 over n plus 1, we get 0. So what did we show? This is a squeeze argument, right? We showed that the remainder term goes to 0 for any x within that radius of convergence. And so because the remainder term always goes to 0, we have shown that this series converges to the actual function. Any questions on that? Anyone still writing? Okay, so we've only got about 10 minutes. So try to do some group work and talk some of these out. Let me paste this matching activity. So maybe if you guys want to still practice these remainder stuff, feel free to work through the rest of this activity. Otherwise, I mean, you can feel free to look at the project for today and messing around with some of these Taylor series. Or if you just want to spend the next 10 minutes kind of looking over these matching activities, might be a good thing to do. Match your Taylor series with the expansions and with their sigma notation form. Similar practice to what's going to be on the project today.